Hi, this is Lauren Mitros. Today I will be solving heat transfer problem 1.19 from the 8th edition of Fundamentals of Heat and Mass Transfer by Bergman and Levine. So 1.19 states that a square isothermal chip is of width W equals 5 millimeters on a side and is mounted in a substrate such that its sides and back surfaces are well insulated. The front surface is exposed to a flow of coolant at T infinity equals 15 degrees C. From reliability considerations, the chip's temperature must not exceed T equals 85 degrees C. If the coolant is air and the corresponding convective coefficient is H equals 200 watts per square meter Kelvin, what is the maximum allowable chip power? If the coolant is a dielectric liquid for which H equals 3000 watts per square meter Kelvin, what is the maximum allowable power? So first, we're going to write down our givens. So first given is W equals 5 millimeters. We know that the system is well insulated, that T infinity equals 15 degrees, that T max equals 85 degrees, that the convection coefficient of air is 200 watts per square meter Kelvin, and the convective coefficient of some dielectric liquid coolant is 3000 watts per square meter Kelvin. Now we're going to look to find the maximum allowable power for each coolant, or at each H. So let's draw a diagram. So first, we're going to draw the side view of the chip. We know that the chip is isothermic and sitting on a well-insulated plate. Now we need to draw the coolant around the chip at some temperature, T infinity, and some H. We know that the only mode of heat transfer involved is via convection, and that the width of the chip is W, and that the maximum the chip will achieve is 85 degrees Celsius. So our assumptions. We can assume that the chip is operating at a steady state. This means that nothing is changing about the properties of the system, including the temperature of the chip. We can assume that energy is conserved and that the chip is well insulated on the bottom, meaning that there is no loss through the plate. Therefore, no conduction. We will also assume no radiation. Finally, we're going to assume that the chip is of a negligible height, meaning that there is a negligible amount of heat loss through its sides. So finally, our equations. We are looking for the maximum allowable power in the chip, which is measured in watts. There's no other sources of energy associated with the chip other than thermal energy of the chip generating heat and then losing it to its surroundings. Because of our assumptions, we know that there is no conductive or radiative heat, only convective heat loss. The only equation we are going to use for this problem is the convective heat transfer rate, which is measured in watts. So now we're going to go through and actually solve the problem. So for air cooling, we know that the Q convection is equal to the convective coefficient of the air times the surface area of the chip times the difference of the chip temperature and the surrounding air temperature. We get a final answer of 0.35 watts, making sure to cancel our units. Next, we can do the same thing with the dielectric coolant, making sure to use the convective coefficient of the coolant rather than air and keeping all values the same besides that. We get an answer of 5.25 watts, which is nearly 10 times more than the power allowed, which is nearly 10 times more power allowed than what was allowed with air cooling. Now for some comments. So why didn't I convert the temperature from Celsius to Kelvin? So both have the same size degree. The difference of 85 degrees Celsius and 15 degrees Celsius is 60 degrees Celsius. Whereas if we were to convert that to Kelvin, we would get the same 60 degree temperature difference. So the magnitude of the difference is the same, even if the units aren't. Now, converting gives us less opportunity to make simple mistakes in our work. But if you don't feel comfortable leaving it in Celsius, you can always convert it to Kelvin. So that will conclude this walkthrough. Thanks for watching.